Hi friends, let's have a look at problem 2909 and problem 2908. So minimum sum of mountain triplets. So this is the second. So for problem 2808, the only difference is that the latter have a smaller problem size. But in this problem, the problem size can be as long as 10 to the power 5. Therefore, the solutions here will automatically solve problem 2908. So we are going to focus on this problem solely. So our plan is the following. So in this video, we are going to explain the simulation solution based on min heap. And after this prerequisite, in a follow-up video, we are going to present a solution based on linear scan. Actually, we hope that you can follow the whole video series so that you can get the full range of techniques, and also you can digest the optimization procedure. So with that said, let's look at the problem statement. So here we are given an array called nums, and a triplet of indices is a mountain if they have a strictly order, and also the middle one is larger than the two sides, right? So we are required to return the minimum possible sum of a mountain triplet of nums. If no such triplet exists, we're going to return -1. So here we have 3 examples. In the last example, we do not have triplet mountain, so we're going to return -1. And in the first example, so we see that we have 1, 5, 3. So this is the minimum possible, right? So we're going to have none. And in the second one, we are going to have 7, 4, 7, and 2. So the sum is 13. But we have other mountain triplets. For example, you can see 8 and 10 and 2, right? So this gives you 20. But we want to return the minimum possible sum. So with that said, we are ready to do the coding part. So here, the sort is very simple, right? What we want to check, so for each index, so if we want to use I as a potential mountain peak, right? So let's call the middle one. So here's nums G as the peak. Then we need to know the left side smallest one, right? And the right side smallest one. So our focus will be on find the minimum number to the left of I and to the right of I if have, right? Or if exists. So then we are going to get a sum for the mountain, right? So we just need to check all the indices and then return the minimum one if possible. So now let's do the coding. So this, we just need to translate this observation or this idea into coding format. So first, let me find left smallest for each index, right? So here I can do something like this, right? So so here n is the length of this nums list. So because at the index 0 there's no left, so we are going to set that to be float infinity. So this is due to adapt the problem return because we want to return minimum possible sum. So now let's do the iteration. Maybe we can do this. Let's see. Smallest, we could just use empty one. So we can use heap. So we can make a heap and heap q, heapify this guy. And then we are going to do iteration, right? So for I in range n, right? So at the very beginning, so for index 0, there's no left. So we want to put positive infinity. So basically, if not heap, then what we want to do is left smallest. So going to append float infinity. So as we mentioned, this is to adapt the problem return. Otherwise, the heap is not empty. So we want to get the smallest, right? So we just left smallest. So we append. So because we are using min heap, at the root of the heap, or heap 0 is the smallest number. So afterwards, so we want to do heap heap push, right? So we push the current number nums I into the heap. So this way, each time when we look at this index, we are going to get the smallest number to the left of I. So you can print out this left smallest just for an examination. So for example, here 8 to the left, so no element, so we corresponding to infinity. So to the left of 6, the minimal element is 8. So here we have 8. And for 1 to the left, so the minimal is 6, so we get 6. For the 5, so to the left, so the minimal is 1, so we get 1. And for 3, the left, the minimal is 1. So in other words, we have infinity, 8, 6, 1, 1. So this is the one part. So we want to do the same for the right. So let's do it. So right smallest. So we're going to do heap again, right? So for I in range, so we are going to do it from n minus 2, right? So let's do n minus 1. So negative 1, negative 1. So the middle negative 1 is the index which we end before this number, and the negative 1 is a step. So now let's look at if if not heap. So we are going to do this, right? Smallest append, so float infinity. So this is parallel in the left smallest. We are going to adapt the return of the problem. So we put a float infinity. Otherwise, so we are going to get the smallest number to the right of the current index. So we append heap 0. Again, here we are using min heap, so heap 0 is the smallest. So afterwards, we need to do heap q, heap push. Push the current number, nums I, into the heap. So similarly, you can print out the right smallest, right? So let's examine that. So here, to the right of 3, there's no element. So we have, so here, let's see, we want to do something like this. We rather than use append, we use assign, because this, we need to from right to left. So here, let's do something like this. So let's change this to I into float infinity. And so here, let's use I to be yeah, this will be better. Now let's see, we make this order right. So if you see, there's no element to the right of 3, so we have infinity. And to the right of 5, the smallest element is 3, so we have 3 here. And to the right of 1, we have minimal element 3, so we have 3 here. To the right of 6, we have minimal number 1, so we have 1. And to the right of 8, we have minimal number 1, right? So now we get the right and we get left. So now for each, so we want to check the mountains and return the result. So let's use a result float infinity. Again, we are using float infinity is to adapt the problem return requirement. And then for I in range n, right? So let's do something like this. So for a, so a, b, and y in zip, we can use this zip function. So the left smallest, right smallest, and nums, right? So then y will be served as the middle, right? So we want to check if a is less than y and b is less than y, right? Then it means that there is a mountain corresponding to the peak y, right? So then what we want to do is we want to update the result. It means the result state plus a plus b plus y. All right. Then finally, we just need to do the return. So we want to return the result if result is less than float infinity. So this if basically checks if there is a mountain, right? Otherwise, we just return -1. So this actually forms a solution format to this problem. So now let's check it. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes the generic case. But here we actually notice that during our coding, so here we have one, we compute the left part, smallest numbers. And here we compute the right smallest number. So there are some redundancy, right? We repeat essentially the same procedure twice. Therefore, we can make this more modularized. Let's write another solution format. So this can be regarded as a optimization, right? So here, what I want to do, I want to write a hyperfunction called to get the smallest, so that I can call that function to get the left smallest and the right smallest. So let's do this. So let's get smallest. So what we want to accept is nums. So either we get left or right. So let's assume we get left. And then first I get the length of this nums. And then I just need to write the above logic. So in other words, this part and this part into the same function. So let's achieve this part by using assignment. So we have a float infinity times the size. And then I want to start end. So if and step. So if left is we want to compute the left, we need to start from left to right. The start will be 0 and end will be n-1 and step will be 1. So this is for left, right? So if not left, so we are going to start from index n-1 and ending at index 0. So the step will be -1. What we want to do is start and end. We just swap that. And then we multiply step by -1, right? And then we can do the assignment. So this actually is very simple. So what we want to do, we can either do assignment or we can use heap. Let's use heap in this problem. So here, so we use a heap and heapify it. And then we iterate. So for I in range, so start, so end plus step and step, right? So no matter you have left or right, so the assignment will be right. So if heap, so what we are going to do, we are going to set result I equals heap 0. So this will be the smallest, either to the left of index I or to the right. And afterwards, no matter what, so what we are going to do is we do heap push the current nums I. So here we push in this heap. So what we want to return is just the result. So notice that here, if not heap, basically we want to set it to be float infinity according to the first version. However, we have initialized as float infinity. So we just check if heap is not empty, right? Otherwise, the main operation will be this. And this will give us the hyperfunction. So now let's look at the problem logic. So let's first get the left smallest. So it's going to be get smallest nums left equals true, right? Then we can get right smallest. Let's copy this line and put it here. Let's change this to be right, and the left let's choose to be false, right? So now let's print out this again. Left smallest, print right smallest. You can see this will be the same as the previous problem. So now once we have this two part, and we can copy this part. let's comment out this one. So now let's do a test. Yeah, it passes the first example. So I guess we have changed this function signature. Yes. So we are checking this solution. So now let's look at the generic case. Yeah, it passes all the cases. So now let's first do a time complexity analysis, and then we want to comment further. So here we have two for loops, here and here. And then these two for loops have the same time complexity. So then in each loop, so we do an end round, right? So each round we have a heap push operation. We have a append operation. The append operation is O1, and the push operation will be O of k, where k is the heap length, right? So originally we have 0 elements, so heap will be 0 and then 1 and 2 up to n-1. So overall we need this number of operations, 1 plus c. We start from log 1, and then in general it's 1 plus log k, and then so we have 1 plus log k minus 1, n-1. So here the log, we can regard the base as 2, but you don't need to care about, it's just up to a constant. So then we have two parts. One is we have n-1 ones, so the total is n-1, and then we have log 1 plus log 2 plus log n-1. So the latter is nothing but logarithm 1 times 2 times say n-1. Actually, if we do it in roughly, we can write it up to n, right? So this logarithm is nothing but logarithm n-1 factorial, right? So here now we can use Stirling's formula. So here Stirling's formula says that this is roughly n log n minus n plus 1. But you can drop this one just for a rough analysis. So this part is nothing but roughly n plus 1 plus n minus 1. Listen, here n minus 1. Anyway, it does not matter. So n minus 1, so times logarithm n minus 1. So minus n minus 1 plus 1. So roughly n minus 1 logarithm n minus 1. So we can write the complexity as n logarithm n. So this is the time complexity. But the interesting part for this format of solution is that so we are using the heap to do a simulation, and in between, so the essential thing is to find the smallest number to the side of the current index, either to the left or right. So if we inspect the solution, so actually when we do the smallest numbers to the left and the right, we don't need to use heap. So we just need to use some running variable to do it when we do a linear scan. So this will be the topic for the next video, a follow-up video. So we are going to solve this problem using a linear solution, so just a pure linear scan. But this format here is also useful because the heap actually can be very useful for addressing a number of different problems in LeetCode. So with that said, that's about it for the current video in order to control the length of the whole video. So in the follow-up, we are going to explain the linear scan solution. Thank you.